Okay, so good afternoon, everyone. So good evening rather. I'm just gonna give a bit of a brief introduction to the Julia programming language. As Prof mentioned before, we actually use the Julia programming language um in the operations research course for the MSc in data science. And in addition to using it, there Dr. Kalicharan, before he passed away last year, also wrote an introductory textbook to Julia. Okay, so Julia is a programming language, and so what it is core is a programming language, right? And its core programming language is really just a way to specify some computation, right? It's a way for you to actually just basically pin down the implementation of an algorithm and some data structure in a way that in principle should be realizable on some sort of machine, right? A programming language is considered Turing complete if any arbitrary algorithm, any arbitrary computable function can be specified in said language. So like Julia is an example of a Turing complete programming language, so is C, so is Python. But then you have, say, languages such as SQL, which are not Turing complete because there are computable functions that cannot be expressed in SQL, right? So there is an interesting point that, there are some computations that just cannot be expressed in certain languages, right? It is impossible to express those computations in particular languages. So that's raises the question. So aside from this dimension of being Turing complete or being not Turing complete, are there other bifurcations we can make that we can use to differentiate different programming languages, or decide which programming languages are better? And all programming languages are not created equal in regards to their particular application domains. So this is a quote from Ludwig Wittgenstein. He was a philosopher at Cambridge, and he was very much concerned with language. And he has this famous phrase that the limits of my language are the limits of my world. And in linguistics, this is codified into a hypothesis called the Sapir-Whorf hypothesis, that basically pretty much captures what Wittgenstein said, that language just sort of limits your thoughts, your ability to think. Your limitations of your language sort of can inhibit or actually help you in terms of actually problem solving, in terms of thinking. There's some interesting evidence for this. For example, there's some evidence that languages that lack explicit words for certain colors, that people who speak those languages alone, they actually experience colors differently than people whose first language actually have explicit themes for certain colors. Like blue is an example of one such color. There are some languages that actually don't have an actual indigenous word for blue. So they actually experience the world differently because they don't have an indigenous word for blue. And this actually applies, and I'd argue it actually applies more strongly when it comes to programming languages, where different languages actually lend themselves to representing different computations by virtue of their design, their syntax, etc. Right. So over the course of the last several decades, programming languages have been designed to accommodate different types of computations better through the syntax that they adopt, through the primitives that come bundled with the language, of course, of the idioms that end up emerging as the language finds use in amongst technical communities. Certain programming languages just better designed to handle different types of computations differently. So for some examples, this would be, for example, C, designed for development of designed for systems programming. So the ability to facilitate some degree of low-level memory management and low-level operations. JavaScript was designed for development of web applications, and so its syntax, its primitives, accommodate those sort of the operations that are required of a web application. For example, things like Ajax and the like. And let's say R, which was an open source implementation of IBM's S programming language, was designed for statistics. So like, R has certain primitives, such as vectors, and native implementation for data frames for managing tabular data sets that can bundle with R. So in the primitive example of how primitives are sometimes built into the language to actually facilitate the particular use cases that the language is designed for initially. Right, and there have been a couple programming languages that have become popular in scientific and numeric domains. R, again, being one of them, specifically in statistics community. To this day, a lot of let's say different statistical procedures that are created are still written sometimes first in R before they're ported across the different programming languages. Fortran is kind of interesting in terms of scientific and numeric computation, because Fortran actually disallows pointer aliasing, which actually allows it to make some interesting vectorized optimizations under the hood, which is why to this day the Fortran implementation of certain linear algebraic procedures are still considered the most efficient. MATLAB, of course, it stands for Matrix Laboratory. So, matrices exist as a primitive within MATLAB. It has a lot of the common, linear algebraic functions built in. Python was not initially designed with scientific programming in mind. It's a scripting language first and foremost, but its design ended up winning the favor of people within scientific numeric domains. I know a lot of libraries are built around Python to help enable it to be useful in scientific numeric computing. Of course, such as NumPy, Pandas, Rapids, etc. And each of these languages would have their advantages and disadvantages due to their design as well as their canonical implementation. So I mean by canonical implementation, when you think Python, people, it's interesting when you want to think about Python, the programming language, or you want to think about Python as in the implementation of the Python programming language that you'd run on your machine. So like the Python implementation, the Python interpreter you download from python.org. That's what I mean by the canonical implementation. So because anybody can basically take pretty much any programming language specification and implement an interpreter or a compiler. But there are canonical implementations that we usually use as sort of like a synonym for the language itself. But just strictly speaking, these are different entities. All right, so there are a couple of advantages to design of some of these. Python, there's a global interpreter lock, which actually inhibits some forms of parallelism. R, it has one little design warts. Like R has like 3 different ways to do object-oriented programming. So sometimes if you're building certain things that, like say you're building scientific numeric applications that have to be deployed in industry settings, sometimes R is really not that suitable for it. Because of that, like MATLAB and Fortran, they have their own little issues in terms of what features they've implemented, etc. Julia is a recent attempt to improve upon these previous approaches. Design language that's supposed to try to take what the creators of Julia believe each of these different languages did well, and to basically create an amalgam of these design choices and principles, etc., as well as to bring in some of the the latest trends really in how we design programming languages. Right. So how is Julia better in some regard when compared with some of these other previous languages? So one of the first things to be that the implementation itself, the canonical implementation, is well designed to exploit just-in-time compilation on a low-level virtual machine backend, right? So the LLVM backend has become rather popular for as a backend, a bytecode backend for designing a lot of modern programming languages. And Julia uses just-in-time compilation, which would use information as as the program is executing to help make certain optimizations, which actually helps the Julia compiler compile the Julia high-level Julia code to the most efficient LLVM bytecode that it can. And that helps to achieve high performance. So like in all, with the exception of Fortran, in Python, MATLAB, and R, you're told to avoid for loops, right? And for good reason. Python, MATLAB, and R, they kind of depend on vectorization to get stuff done efficiently. But with Julia, you can get good performance with for loops. So you don't need to find weird or interesting ways to try to vectorize your code. If a for loop really is the most natural way to express the computation you'd like to express, you can express it in Julia, and it'll be fine. You don't have to worry about taking a whole day to run through like a for loop, like they say over like say some sort of like 5D tensor or something, like you would in Python. Like you can get fairly good performance there with Julia. And so this is a chart that that actually is there on the Julia site, where it just show a comparison with different functions that would actually compute these sort of tasks that you would actually perform in scientific computing. And if you look at those times there, Julia is there performing rather well when compared with, say, R, Python, MATLAB, and Mathematica. It's performing at a level that's actually approaching it's close enough to see that it should be considered impressive, right? And it even outcompetes Fortran with certain operations, right? So this is the hammer home that Julia, the in terms of implementing Julia, the implementers have done a really good job of exploiting, let's say, modern programming language techniques to be able to have a canonical implementation that generates efficient bytecode that can run pretty quickly and not consume too much memory, right? Another aspect of Julia that actually makes it pretty nice, and Prof alluded to this before when he mentioned we used it for optimization, for the optimization portion of the OR course, is that there's a powerful macro syntax that allows us to actually build in these nice, neat, nifty, scientifically oriented domain-specific languages. So JUMP is actually the one of those libraries that exploit the macro system. Okay, well, I should probably actually sorry, I just realized got ahead of myself. So basically, a macro in a programming language is a means of specifying a way that the syntax can actually be dynamically modified at runtime. So you can think of it as a function that operates on the syntax of the language itself. So that allows you to dynamically extend a language. Different languages have their own macro syntax. Most famously Lisp. They actually have it actually have pretty great macro facilities in Lisp, as well as its descendant languages. In C++, you can kind of jerry-rig some aspects of this using template metaprogramming and the like. But with Julia, it's actually sort of a Lisp-inspired way of approaching macros. So it's quite powerful. I mean, we see some examples of it in a bit. And there's also some useful primitives for scientific computing. So vectors, matrices, different numerical types, etc., all come bundled within Julia, and you have appropriate syntax for manipulating them, working with them. So it's very much batteries included from a scientific and numeric standpoint. What's also pretty neat is that it actually enables us to use LaTeX when we are defining variable names or function names, etc. So you can actually have mathematical symbols embedded in your code pretty easily. And you know, especially like if you're writing a paper, and you want, let's say, your equations to match it in your code to match up. You know, well, this is pretty easy to achieve in Julia, even when compared with, you know, other programming languages. I mean, yes, and yes, it's true in R and Python, you can just use a Unicode and put the scientific symbols in, but with Julia, it's a lot easier process, which we'll see in a bit. Right now, not everything is all sunshine and rainbows. You know, while I'm talking about Julia, I have to make mention of that. So one issue, this is a bit opinionated, I suppose, is that personally, I'm not too fond of Julia's the project structure that Julia sort of encourages you to set up. I really think, especially for scientific and applications and data science applications, I think Python got a lot right. Even though it wasn't initially designed for that, it ended up doing things that, from our standpoint, is quite helpful. And I personally find like the Julia system for how our project structure is set up to be a little unwieldy. And I could see, like, for beginners who, well, I shouldn't say beginners, but people who have programming experience who are trying to get into Julia, how the project structuring might be a bit unintuitive. It feels a little too much like Java, personally, to me, that I would like. The community, of course, is not as large as with Python or, I mean, Julia is a fairly young language. I believe about right now, it's probably about 10 years old. Python has been around for more than twice that, and R has been around for a very, very, very long time. So, you know, of course, the community just wouldn't be as large, although it has grown quite a bit even in the last like year or two. So, you know, it's still, it wouldn't just be walking to an empty room. There will still be people there, just not as much as with Python or but because of there's a small community, you know, sometimes the packages and the ecosystem, they need to catch up a bit with, let's say, Python, or for example, the agents.gl, which is the library in Julia for agent-based simulations. They need to catch up a bit to the Python offerings. I mean, they actually, in my opinion, much better designed. But in terms of the functionality that's offered, they do need to catch up a bit. And of course, you know, you have the tidyverse in R with diplar and the like. And, you know, while you have things like query.gl and data frames meta, that actually manages to achieve some of that same, you know, tidyverse as diplar approach to manipulating data, it's still not at the same level as diplar just yet. And of course, resources need to catch up. Although, of course, there've been, you know, a couple. It's gotten, you know, it was a lot better within the last year or two. You know, there's actually a book. But of course, you know, there's Dr. Kalitran's book. There's also a book on operations research. You actually programming for OR using Julia. So, you know, the resources are being built up slowly but surely, and the IDs need to catch up as well. There's no PyCharm equivalent really for Julia yet. There's Julia, excuse me, there is a Julia extension for VS Code, but it's still not at the level of let's say, you know, things like PyCharm, you know, that you know, you might be a bit more accustomed to if you're coming from more Python background. So just a brief few miscellaneous details about Julia before we start looking at some code and start playing around with some code. It's in terms of typing discipline, Julia is strongly typed. So pretty much this means you need to do a lot more overt casting. It's not like, say, OCaml level where if you have to use different operators for different types like that. I mean, there's a lot of there's some good polymorphism implemented in Julia through multiple dispatch, but you do need to cast and be at least aware of your types in your code. But on that note, Julia is a gradually typed language, so there's no need to specify the types before executing. Though they can be beneficial because they act as a form of documentation within the code, and they actually can sometimes help make code more efficient. So sometimes when the JIT can actually sees that, you know, you're expecting an 8-bit int, for instance. It knows it has to optimize around 8-bit ints alone. So it's not going to bother to implement or to make optimizations for other types, and that can help the code be more efficient. I mentioned before, it uses multiple dispatch, which helps implement polymorphism, which pretty much means that the exact version of the function that's used is contingent on the signature of the function. It's homeoconic, like Lisp, which basically means that a language is represented internally as a data structure that it can manipulate itself. It's a procedural language, so no object-oriented programming here. There are some functional facilities, of course, as pretty much any modern programming language would have, but there's no OOP. So instead it takes an approach where if you want to like bundle things together, you use structs, and you exploit multiple dispatch. And it's an array language to some extent, not to the level of MATLAB where you know everything's an array, but it is a programming language that you know is designed with be able to manipulate arrays, you know, as proxies for vectors and matrices and tensors and the like. So right, so that's there's a high level overview of Julia. So with that, we can now start going to some code. Right, so let me just pull up. Right. So firstly, I'll just show like just very briefly what I mentioned from before. That you can actually type, let's say, latex symbols inside of Julia. So let's just say you want to let's say you want to set epsilon, you can say epsilon should be small. Right, so you can actually like they actually type these mathematical symbols in here and the like, and pretty much you have access to the entire Greek alphabet. Sorry. Right, as well as different operations such as in. There's a for all as well, etc. There's also false. I know I have to import that one. That's a separate thing I would have to import. But yeah, so you can actually get like the full you get the usual mathematical symbols inside of the inside of your code. In terms of types, you can inspect them using type of. So the CSCA tree, it says an int64. So one thing with Julia is that it uses 64-bit ints and 64-bit floats as default. If I do this, let's say it's float 64. But I can cast if I dead set using an int32, I can do that. I say type of x, right? It says an int32. Of course, as you would imagine, you'd have your usual super arithmetic operators. So I mean, there's no point really going into that. Power, you know, it is represented by the standard caret symbol. So you know, you can in Python you'd use the double asterisk to say power 2. In Julia, you can just say you can just basically use the usual caret. symbol to indicate the power operation. Right. Now, one thing to note, of course, is that because these are scope in terms of bits. Let me see if I can force overflow. That's not what I was expecting. Sorry, I was trying to force overflow. Yeah, in this case here, it just getting 0 now, but trying to actually force the overflow well. There's also, of course, a big type. Right, for representing big ints, which would behave a bit more like Python integers as well. Right. Now, of course, you might be asking, okay, well, if this is how you implement power in Julia, how do you implement XOR? So if I say XOR, so you implement it. It's actually, so it's an XOR function that you'd have to use in Julia. But otherwise, you have you pretty much have your bit shifts working pretty much like you would in C. Right, so it's pretty much just what you would have in C there. All right, booleans are true and false. Just like in Python, if you want, you can chain comparisons like this. So they're saying 3 is less than 4 and 4 is less than 5. Strings. Now this is a major departure from, say, Python or R. Strings are single quotes. Sorry, double quotes. If I was to do this, it would complain, right? So in Julia, you actually have character literals, right? So in Python, you don't have character literals in the same way you would have it in C, but in Julia, you have access to character literals. Right, and no, that's the library that's cool. Right. Of course, you can index into strings, and you can use standard slice syntax, just like you would in pretty much any other programming language. One thing to note, of course, is that Julia is 1 indexed, right? So it's not 0 indexed. It's 1 index, which is something it takes from MATLAB. So that's an important gotcha there, right? There's, of course, there's a string, like any modern programming language, is going to be string interpolation. If I say 3.4, I can do it'll do the appropriate interpolation computation. Same thing works with variables. If I say 3, I could always say false palette. Right? Yeah, it will inject it into your code for you. Right. Just bringing in libraries, you use the keyword using, and example here. Oops. Yeah, come back and see why this one isn't working now. Right, but it should have actually done a string format there, but let me show instead. So this, whenever you see an at in front of what we might think is a function, that's an example of a macro being invoked. So if I say show x is a particular macro that would it would take the variable and say what variable name equals whatever stored in the variable. Right. So this is an example of a macro here. Right now, pretty much a lot of else what you see, pretty much what you see in any other programming language. Now, an important element that I mentioned before would be arrays. So if I want to create a 1D array, right, I'll just use commas as I would in any other programming language, right? This is actually printing it in a columnar fashion, because it's seen as a vector, right? So in linear algebra, vectors are considered columnar vectors by default. If I do this, right, I get a row vector, and a row vector is actually considered a type of matrix. Right? If I say right, and here, of course, is broadcasting. Just like in NumPy, you get broadcasting here to actually compute the this broadcasted matrix. Of course, if I want, so if I go to, right, this here wouldn't work because it's not seeing an appropriate shape to broadcast to. But if I say I want to do element-wise, the element-wise product, I just introduce dot here. And likewise with plus, I can have the element-wise addition, etc. So this dot notation here is actually pretty nice, because this is actually how you can achieve it's a syntactic sugar for element-wise application, pretty much. So if I was to say cosine of 2, right? If I say cosine of 1, 2, 3, right? It won't work. But if I say dot, it would know it has to broadcast this cosine operation across these 3 elements here. All right. Okay, well, and then let's say I have this vector. Let's go back here and create another vector. Now, a convention in Julia is that when you have a function that modifies an array, it would have an exclamation point at the end of its name. So push here modifies the array vec. So because of that, it would have an exclamation point at the end. Now, this is as a naming convention. It's not to say that, by putting an exclamation point at the end, it's going to magically transform the function to one that mutates state. But it's a naming convention that's within the Julia language, and it's one that's very closely followed. There's an n keyword that would get the last element of a particular vector, which is pretty much what you would it's like your -1 in Python, etc. So it pretty much would have like pretty much the same operations that you would expect in pretty much any other programming language. Dictionaries. Right, so there's a special syntax for dictionaries where you just use this here as a sort of a mapping indication. And the 1, of course, it'll pull 1. Now, what's oftentimes used in Julia is this concept of a keyword. right? And the type of it'll say it's sorry, symbol. And this is pretty much like this is adapted from Lisp. And the idea here is that this is just used as a symbol. It's not a string, although you can convert it to a string if you wanted to. But so it's oftentimes used for keys of constant dictionaries. Of course, you have your standard for loops. And in Julia, if you want to end a block, you see end, right? So it's as opposed to Python, which uses indentation, and R that would use curly braces. Julia uses an end statement to end the block. So I want to show I print this here. And if I want, I could actually use the symbol for in, as opposed to using the in keyword. I can use the symbol for in. That would actually say for I in 1 through 10, do this. Okay, right. So that example they have like where, I mean, syntactically otherwise, it's pretty much like what you expect from a regular programming language. But what I can do now is go show some examples of what we might use Julia for. So this example actually from the OR course, where we tried to solve an optimization problem. So how these would usually work. Let's say if you wanted to put into another solver, that you have to learn the particular syntax of the solver. You have to specify it in that syntax for that solver, and then you'd have to then call that solver. What this library jump does is that it imposes a consistent syntax through macros in a domain-specific language embedded in Julia, and you can simply specify and then just instantiate a particular solver, right? And just call the solver to actually solve the optimization program. So this actually would convert this. So that we're specifying our optimization problem, right? Which is close to our mathematical specification of the problem. And the jump library would handle the rest of the heavy lifting to actually convert it into a form that the underlying optimizer can actually use. So if I was to run this, all right. So here now you're seeing how it's oh no, why? Okay, it's not supposed to do that. Sorry. Yeah, it's not configured properly still. All right, let me try solving it from terminal then. All right, sorry about that. It's like I guess it's for some reason it's not working well with the notebook right now. So I just copy paste this code. Okay, it's sorry, yeah. Sorry about that. It's apparently some configuration issue with my machine still. It's not I guess the library didn't install properly. Okay, so sorry about that. This is another example of an optimization, some code for optimization for a particular paper, and how this would work is that here this uses a library called convex. And how convex works is that it's similar to jump. You specify the problem. So here we actually create and specify an optimization problem. And how convex works is that once your problem just uses the primitives within the convex library, your problem is guaranteed to be a convex optimization problem. Because it's guaranteed to be a convex optimization problem, you can use different solvers or optimizers that are designed for convex optimization problems to actually solve the problem you're specifying. So in this particular case here, this is a second order conic problem. So we actually use the SCS solver to be able to actually solve it. Right. In terms of other macros you can actually use in Julia. So this is actually a pretty nice one for GIFs. So let's say, for example, you have a series of plots. I want to combine those plots into an actual GIF that can actually you can actually download or use, or just for display purposes. You can actually do so just by using the GIF, the @GIF macro. And this with any for loop, once there's a valid plot command in it, it would actually construct a GIF for you. So you don't actually have to go and do anything else. You pretty much just get this ability to construct a GIF for free. Another useful library is this one called benchmark tools. So what it allows you to do is that it would actually allow you to benchmark a particular computation, and it will actually tell you how long it took and how many bytes were allocated. So this is actually useful if you have to benchmark some code to whether it be you have to do timing experiments for a paper, or whether you have to you're trying to make something more efficient. Benchmark tools is really helpful for that. This is an example of the data frame library I mentioned. That's the diploid replacement. So here we just basically have a data frame. That's the iris data set, and we can use macros to actually specify something like a query that would actually that we can that looks almost as though it's like almost like a SQL query almost, with embedded within Julia itself. So that makes it a bit easier to do some data frame manipulations. The last one, unfortunately, this one is taking a while to actually run. But this one, what this one would have done is that this actually runs what's called a Gibbs sampler to actually fit a hierarchical Bayesian model. So here you actually can actually specify, say how this is distributed as this particular distribution, etc. And you can specify your model, and you can use Gibbs sampling and the other different techniques of fitting hierarchical Bayesian models, and usually fit the model and learn the parameters of the model. But this one is unfortunately not. It's causing the notebooks to crash. I have to check and see what's wrong with this particular configuration. So I think that's pretty much it I wanted to show. Anybody have any questions?
Thanks for that, Inzamam. Yeah, nice introduction there. Yeah, Nicholas has a question.
Yeah, sorry, the examples.
That's normal.
Yeah, I'm already surprised to see a malloc issue come up. I didn't know I called like that. I have to reinstall it again, I guess.
Neat stuff. I remember I did a bit of the OR course, and I remember seeing that ability to represent an optimization problem, and it would just run it for you. Is that something that only Julia does natively, whereas the other programming languages have to use like a library?
But with Julia, you have to use a library as well. But the
it is a
difference
library,
between
okay.
Julia is that, like, how we can get these nice macros, we can't get that within another programming language. There's, I mean, there in Python you can sort of get some of it, but it won't look as neat. It won't look as nice, and it I mean, people say like, okay, maybe it's just aesthetic, but it's not just an aesthetic difference, because it helps to think in terms of the mathematics of the problem and to concentrate on that in a sense. That takes off a degree of cognitive load, and you just concentrate on specifying. So it's really power. And why Julia is what you really do this in is because of these macros, which is an inbuilt feature of Julia.
Okay. And another question. Is Dr. K's book out?
Yes, it is.
Awesome. That'll be in the UE
but-
library, though.
I'm not sure, but fun fact is that while I was just checking over something in the Julia site just to make sure I got some of the details right for this, they actually list his book on
Wow.
the official Julia site now
What?
as a textbook for Julia.
What?
So yeah, so if you go there, you'll actually see like on the resources tab, like of the site where they
Wow.
recommend resources you can use to learn Julia if you want to teach Julia in a
Wow.
university setting. They have Julia bit by bit there.
Wow. All right. And finally, I want to get a feel of what's something you would go to Python for because Julia isn't that mature yet, the support,
Neural networks.
network stuff.
Anything to do
Okay.
with neural nets? I prefer to go with Python. Because of the libraries.
PyTorch.
There's one for Julia called because of Python. I mean, there is torch.jl, which is just basically tries to wrap around Python itself, but it's not where it's not where it's actually more convenient than just using Python itself. As like it's like another case where like a case where the opposite would be where I prefer Julia to use Julia strongly would actually be, well, aside from these optimization problems, would be like certain types of computer simulations. It's just because there are times in a computer simulation where you can't vectorize things. You have to loop over stuff. And with Julia, because of you don't have to be afraid of for loops. Julia is like what I'd go to write like a complicated simulation. In terms of like for some ML tasks, I would probably still go with Python simply because the libraries are more mature. People are more likely to be more familiar with it. So like if you're working collaboratively with a team, it's a better choice because the dividends you get from moving to Julia, if they wouldn't be that high enough to justify the sort of social cost within a team, the marginal returns. But like the thing is, like when it comes times for anything to do with optimization or like complex computer simulations, Julia would definitely be what I would go to, because definitely the gains you get are more than substantial enough to justify any loss, any lack of expertise within a team, simply because how well it handles those problems. Anything to do with ODEs as well. I maybe I should have showed that as an example. There are some there are macros for specifying ordinary differential equation problems and PDE problems, and the solvers are there. So it just like what Jump does. It just basically calls the appropriate stuff in the back to solve. But yeah, it's actually pretty good at that as well. I mean, in data science, I don't find myself. I never had to find myself actually doing stuff with ODEs directly. But if I ever needed to, I kind of know where I'd want to, which would be Julia as opposed to the Python.
Right, cool. Thanks.
Yeah, it's also easy to use. I mean, like I was doing a paper with Victor in maths, Victor and what's the girl's name? I forget her name.
Was it Rhea? Rhea?
No. Alana, yeah. And it was optimization, scheduling, and they learned Julia and used it to solve the problem, and we published. So they were able to ramp up quick enough to get it done for the publication.
I guess an interesting part where maybe Julia could be used more, but I don't hear it being used more, might actually be in fluid mechanics and computational fluid mechanics. I don't hear about it much there, but I figured out I mean, I guess everybody's kind of tied to their Fortran code that they wrote like 40 years ago and still works. But I guess if they want to move to sometimes more modern programming language, they could, I guess Julia might eventually have a niche there.
That raises a question about so like I would have Python and stuff. These wrappers in Python to go to other runtimes and so on. We can do the same thing in Julia.
No, it's I think I don't think it exists in Python because of the problems inherent in the canonical implementation of Python. But because Julia doesn't have that problem, it sidesteps that issue entirely. Now there's a C interface and a Fortran interface though. So I mean, but like you see how you have Python, where it's kind of like it's a spin-off, almost like a spin-off language from Python and stuff. It's not like that. It's just like a foreign function interface.
Okay.
That uses, because to some extent actually Julia kind of piggybacks off of Fortran for some things. Like I believe it uses this Fortran package BLAS under the hood. So it has like a way it connects into BLAS and it calls some linear algebraic operations from inside there. For things like eigenvectors, eigenvalues, etc. Determinants, that kind of stuff.
Okay, cool.